So what are we in fact doing today? All right. Boykanyo, the topic of measurement has definitely been covered. You'll see it in the list of topics that we've covered previously. If you just look at the Watobe website, there's a really nice section on measurement. Okay, so what I want to do is start today with explaining to you about formal proofs, because this is what I have set aside tonight for working on. So formal proofs, there will always be one question on formal proofs in paper 2. It'll normally be between 5 and 7 marks. Okay, so that's what we're kind of practicing for tonight. However, my experience in the classroom is a lot of students feel overwhelmed by the detail in proofs, in formal proofs. Just give me a sense of how you feel about formal proofs at the moment. Maybe like a happy face if you're good with them, an unhappy face if you hate them, a middle face if you're like, you know, in the middle. I want to get a feel for the group, how you feel about formal proofs. Okay. It's nice to see the faces there and get a feel for what. Okay. So what I want to say to you is proofs are like a system. And once you notice the structure of formal proofs, it becomes a bit easier. So every formal proof will have something that you're given. Okay. So maybe you'd be given something like you're given a circle with center O, and you're given a chord AB, which is perpendicular to, or let's even say, yeah, it's perpendicular to something like that. So that would be maybe like the normal thing that you're given. Then, and let's even make this like a C. That could be the initial information. Then you're required to prove something. Typically in this theorem, you would be required to prove that AC is equal to BC. This is one of the circle geometry theorems. Okay, so that's step 2. Now, normally this is given to you in the question, but it's just something to be aware of. Then there's the construction. This is where you start your learning, and this is where the marks are available to you. So in this particular theorem, what do you think the construction would be? Just from memory, if you can remember anything. What do you think? Okay, so in this particular theorem, the thing that you need to memorize is to join OA and OB. So this is where the learning work comes in, and normally we'd make that like a dotted line. Now, why do we make those constructions? Well, we are going to use congruency of triangles. So we're going to use congruency, and we're going to use other theorems that we know about. So we're going to use congruency, and that's why we need triangles, and we use other theorems to help us prove the required to prove what. In this case, we're trying to prove that this is equal to this. So I'm going to start with these theorems now, but give me a thumbs up if you understand the 4 basic steps that all proofs are going to have. I just want to see that you have awareness of how the proving game works. Okay. Let's look at what a formal proof looks like. So the question that I just showed you now, here is the given part. You are required to prove that AC, so let's say AC is equal to BC. And the construction is to draw OA and OB. There's OA, and there's OB. How does this now work? Well, you have two triangles, and you say that OA is equal to OB by radii. You say that OC is common to both triangles. And I probably would add something extra here. Actually, no, I wouldn't. And you are given that C1 is equal to C2 is equal to 90. Because remember that you were given that at the beginning. OC is perpendicular to AB. Then you say the triangle on the left, triangle AOC, is congruent to triangle BOC. And what case of congruency is it? It's not side angle side. And the reason it's not side angle side is you've got a right angle, a hypotenuse, and then the other side is the one between here. You don't have the angle between the two sides. You've got a right angle. And so we can say that triangle AOC is congruent to BOC by RHS. Now that you've proved these two triangles congruent, you can then say that AC is equal to BC, and you should actually write triangle AOC is congruent to triangle BOC. That's why you know those two are equal. Now, I'm going to give you a past exam question to do yourself, but give me a thumbs up if you followed the basic logic here, the basic logic of the proof. Okay, now if you didn't follow it, don't stress. I'm going to give you a chance to practice now. So here is a past exam question. You'll notice it's 5 marks. And in the diagram, it says this is all the given stuff. There is what they give you. They tell you to start with that these are right angles, let's say, and you need to prove that RT equals TS. What is my first step going to be? What is my step 1? If I want to get 5 marks, where do we start? So construction, what do I construct? I'm going to construct OR and OS. Notice how they use different variables here. To construct OR, you need to be comfortable with the process. So I construct OR and OS. Now, what's my next step going to be? Well, my next step is going to be to try and prove 2 triangles are congruent. And when I prove that triangles are congruent, there's 3 pieces of information that I have. What are those 3 pieces of information that I need? So Fatejo has told me OT is common. And I agree, Fatejo, OT is common. So I'm going to do that. And I'm even going to highlight it for you so you can see that. OT is common. What else is in play here? I think that OR is equal to OS because of radii. Now, what about the third thing here? What's the third piece of information going to be? It's going to be that T1 equals T2 equals 90. And that's because it was given to you. So you now have 3 pieces of information. You have this side equal to that one. You have the common side and you have the right angle. You now need to write a statement of congruency. So I'm going to say ROS is congruent to triangle ROT, not ROT. ROT is congruent to triangle SOT, and what is the case for congruency? Notice how I also, when I write my angles, I write them in the correct order, like the R goes with the S, the O goes with the O, the T goes with the T. So it's going to be RHS. Yeah. Now, what's my last step? Well, I needed to prove that R2, so I can say, therefore, RT is equal to TS. You can see them there, or if you want to, and the reason is triangle ROT has been proved congruent to triangle SOT. And that's 5 marks in the bag. Thank you very much. Give me a thumbs up if you followed that. Give me a thumbs down if you didn't. Okay. Now, I'm not going to, there is another theorem that's similar to this, but I'm just going to look at it very quickly. And then, in fact, you know what? I'm going to give you a link to all the proofs for all these theorems. I did give you one in the previous lesson too, but I think I want to concentrate today on the theorems that are most likely to come up. But at the same, so I want to give you an actual document that you can have with, let me just quickly share. And so I don't want you to feel stressed about writing stuff down. So here is a link to just a document with just the proofs of the various theorems that you need to know. But I'm going to move on to, this was probably the third most likely theorem. I'm now going to move on to the second most likely theorem that they will ask you. Okay, what is the picture on the board right now of? What theorem does this deal with? What theorem does this deal with? Let me know in the chat. Okay, so we have angle. Oh. Hello? Okay, angle at center is twice the angle at the circumference. Yes. Now, here is one of the challenging things about this proof. Look at the shape. Okay, look at the shape and look at what happens when I move it to this side. Is that still the same theorem? Yes, it is. But look at how it looks different. Like this is like the arrowhead shape. And if I keep moving the angle, the circumference across, it's almost like I get a bit of a squashed thing going on. And then there's also the theorem that we have when we go like this, where the reflex angle is the angle at the center and it goes the whole way around. So one of the things students struggle with is knowing that there's 3 different variations of this theorem. Give me a thumbs up if you can see the first, the arrowhead, sort of squashed one, and then the flipped one. Because I'm going to start talking about this proof now, and I'm just going to explain some of the ideas, and then we'll go from there. Okay, now, if we look, I don't want to get too sucked in. We're going to practice an old exam question for this one too. So the notation I'm using here is a little bit different, but let's start with this. Mitchell, yes, what is your question, Mitchell? You want to unmute Mitchell and we can go from there? Okay, I think there's some technical, maybe it was just a hands up for giving support. So if you look at this setup, you are given a circle with a central angle BOC. So central angle BOC, you can see BOC, BOC, BOC. Look at how it looks different in every situation. And you're also given an inscribed angle BAC, which is here, here, and that one is a bit weird. It looks like that. So you need to prove, in this theorem, you need to prove that this angle over here is equal to twice this angle over here. So that's what you need to prove. What is the construction that you need to memorize? The construction that you need to memorize is simply to draw a line from the circumference to the middle and extend it a little bit. So join AO and produce it to E. Give me a thumbs up if you followed my thinking so far. Can you see the three steps that I was talking about? You can see what you're given, what you're required to prove, and now the construction. Okay, no problem, Mitchell. Okay, now, if you look at what you need to do for this theorem, all that you need to do, I'm not even going to worry about the writing out that they have there. I'm going to do my own little variation of this on the side. So I'm going to draw a circle. And what do I have? I have center O, and I have this like that, and it is up here. And this is going to be A, B, and C. And then what I have is I need to have this, so that would be O, and this is called E. And then we can even call that a 1 and a 2, and we call this 1 and a 2. All you need to know for this theorem, there's no congruency, is if you say, let A1 equal X, what is the size of angle B going to be? So I'll make it a green dot just to make it a bit easier. So if I say A1 is X, what is the size of angle B going to be? Okay, it's going to be X, and the reason it's going to be X is because of radii. All right, now what I want to know is what is the size of O1, which is the angle out here. What is the size of the angle out there? What is O1 using the current thing that we're doing at the moment? So O1, which is the blue dot, is going to be 2x. And how do we know that? It's going to be exterior angle of the triangle. So take a moment. We're going to slow down here because I can see I'm losing some of you. All I'm going to do here is remember my goal is to show that the yellow one is double the size of the blue one. I've done my own little drawing just so that I can draw on it a little bit more, but it's the same as this one over here. I said the green dot A1 is equal to the angle B because of radii. Both of these are radii. Now, what I want to ask you next is if I say to you, using the same idea, let's say that I let A2 equal Y. If I let A2 equal to Y, what is the size of angle C going to be? Maybe I should use a different color for this just so we don't get confused. But here's A2. Now, that's equal to Y. What is angle C going to be? Well, it's going to be equal to Y for the same reason, radii. But now I want you to look at where I just put a red dot, what we will call E2. Sorry, not O2. What is the size of O2 going to be? Okay, so O2 is going to be 2Y, and what is the reason going to be? It's going to be exterior angle triangle. But you know what we found out, ladies and gentlemen? We know, if we look at the top here, we know that triangle, or not triangle, we know that angle BAC is equal to X plus Y. Because remember, green dot is an X, this is a Y. Give me a thumbs up, or if you can see that BAC, or maybe I could even use the, is X plus Y. Okay. And then angle BOC, which is be here, is equal to 2x plus 2y. But I can factorize this and write that as 2 times x plus y. But we know that x plus y is just 2 times BAC, which we got up here. So now we have shown that angle BOC is equal to twice angle BAC, and that's the whole theorem. So the whole theorem just revolves around radii and exterior angles of the triangle. Now, what is a little bit more tricky is that the shape changed slightly over here, but I'm not going to go into that today. I just want to show you a past exam question related to this, but you are going to need to go over the other shapes yourself in your own time. So take a screenshot if you want of my little explanation. I have shared with you some notes, but I think the most valuable thing I can do now is show you what a past exam question looks like on this theorem. So here we go. It's 6 marks. I want you to try and do 10.1.1 first. Off you go. You can do it.
Mr. S, there were 2 questions in the chat.
Yeah.
The first one being, does the IEB curriculum test prove? Because one learner said that their teacher said they shouldn't study for it. And then the other question was, is it possible that we can lose marks for proving it this way instead of the way we were taught?
Okay, so let me do the IB question. I'd have to check, because every school has its own rules to some degree in grade 11. So it is subject to what they do have proofs in IB as well. And so these are generally the same proofs, but it depends if your school has covered all the theorems in grade 11 or not. So that is a hard question for me to answer because your teacher is going to set your exam. The second one is there are actually different ways that you can do the proofs, but as long as the proof is logically sound, you will still get full marks. So I don't want to say you have to do it one way, but the logic has to be there. Okay. But generally speaking, the exam actually gives you normally some of the structure. Like here, the given part is already there. And then what you require to prove is also given to you in the question. So you really start, and in fact, in this one, they even do the construction for you already. So you start at the 4th step. And so all you need to do here to get marks is you're going to have to say that C1 is X, which is radii. So you'll get an X over there. And then you can say that O1 is equal to X exterior angle triangle. And that will give you your 3 marks. Don't leave out the first bit here. Then I want everyone to now try and do this. Try and do the second part. If you know what you know already, you know this is 2x. Okay. What is the next part going to be? So it feels to me like the y is here. So let's see. C2 equals y. I'll give you a bit more time before I think we're almost due our break. We are almost there. So C2 is y, and then we can say O2 is 2y. So we know that this is 2y. And then we can say AOB is equal to 2x plus 2y. And we know that ACB is equal to x plus y. But then we can just substitute here ACB. And so therefore we can prove, we've proved it is equal to, and that's it. So I'm hoping that the structure of this is becoming a bit clearer. Give me thumbs up if you followed that past exam question, like okay, and thumbs down if you still feel a bit nah. Okay, so I hope that what's coming across is that proofs in the exam are normally easier than just learning the whole thing. And there's a very definite structure. The one theorem we learned, we used congruency. The thing that we memorize is the construction. The construction is the key that unlocks everything. And then you need to also memorize what theorems are involved. Now, like if you look at this, what we used here was we used radii, an exterior angle of the triangle, and we used the construction. All right, this is hard work. It does push your brain. So let us take a break so that we can have our concentration back. And so I want everybody out of their chairs, and I want you standing with me. And let's just start with some deep breaths. So in. Oh, doesn't that feel good? Breathe in. One last deep breath. Yeah, then let's shake out the arms. Shake out the legs. Get the circulation moving. And let's do some twisting. So just a bit of a rotation from hips. Start off nice and slow. And then as you feel more comfortable, we're just going to go further. Okay. Then let's just do some small circles. Going into big circles. And then change direction, big circles. Going into small circles. Let's do a tricep stretch. Feels nice. Let's switch to the other side. And let's shake it out again. Shake out the arms, shake out the legs. And then let's get some heart rate. So we're going to do air skipping, and we're just going to do 20. And we'll start in 3, 2, 1. Let's go. All right. Five more. And I hope that your body feels like it's got some oxygen and it's got some blood flow. I hope that that's cool. Okay, I'm not going to do Maths 24 today because I feel like there's quite a lot we're trying to do. So let's go. I'm not going to go through this theorem. It's in the notes. But what I want to talk about is another theorem, which is quite a popular one on past exams. So what this one is actually quite an easy one. So it won't take too long to show you. But what you have here is that the opposite angles in a cyclic quad are supplementary. So you notice how the opposite ones always add up to 180. So as I look at that theorem, have you all seen that theorem before? Now, it is one of the examinable proofs. So I know, Fateko, how will we survive? It is, I promise it'll make a comeback soon. Okay, so let's have a look at how this theorem works. So you'll notice that, like all theorems, okay, there are different steps. You've got the given. What are you given? Well, you're given a cyclic quadrilateral ABCD. So we can see there's my cyclic quad. There are two different pictures, but because of time, I'm not going to go through all of that right now. And you need to prove that A and C, so that's A and C add up to 180. And you also need to prove that B and D add up to 180. So that is what you're required to prove. Now, where does your work actually start? Your work starts at understanding the construction. And what is the construction? The construction is really just connecting the cyclic quad points, or at least one set, to create two radii. So that goes from the center to the edge, and that goes from the center to the edge. Give me a thumbs up if you understand that you just have to create radii for this construction. Okay, so one of the questions was asked in the chat about notes. So at the beginning of today's session, I just shared a link to the formal proof notes that if we run out of time or you feel like I'm going too fast, you can go back and look at these notes that I'm working from at the moment. Okay, so let's look at how the proof goes. Now, the reason you draw these radii is you're trying to create an angle at the center situation. So like almost like the arrowhead. So let's look at what we can see. We see M1, and M1 is, let's get rid of all this other stuff which is distracting. So where is M1? M1 is the reflex angle over here. And what we are going to say is that M1 is twice the size of angle A. So M1 is related to this A over here. It's twice the size of angle A. And see how in this theorem, where we're trying to prove the opposite angles are supplementary, we are using a theorem that we've proved before. Okay. So it's, you do need to memorize what theorems you're allowed to use, but you cannot use a theorem that you're trying to prove. You can't use it in itself. It has to be kept separate. Okay, other bit, M2, so where's M2? M2 would be here, and M2 is twice the size of angle C down here. So those two are connected. So M2 is twice the size of angle C. All right. Now, do you notice that M1 plus M2 is equal to, let me write this down. So M1 and M2 are just going to be equal to 2A plus 2C. Take a moment and see if you understand that. So remember, M1 was equal to 2A, M2 was equal to 2C, and so we can make that statement over there. And it's not, some of you might struggle to see that. Just take a moment and give me a thumbs up if you follow that. because you're using the fact that you've got double, so the angle at the center is twice the angle at the circumference. Okay, so we've done that bit. But now what you notice is that M1 plus M2 make the angles of a full revolution. We know that that's 360, and that would just be because of the angles in a revolution. So angles in, or you can just say revolution, actually. Revolution. Okay, but now if M1 plus M2 is 360 and 2A plus 2C is equal to M1 plus M2, we can then say that 360 equals 2A plus 2C. And if we divide everything by 2, we notice that A plus C will be equal to 180 degrees. So what have you done so far? If you were memorizing this, you were going to say, I basically describe each of the angles in the cyclic quad on opposite sides in terms of being double the size. And then I use the angle in a revolution. But now we still need to prove, we've proved that this one and this one add up to 180, but we still need to worry about that one and that one. So how do we do that? Well, we know that in any quadrilateral, it adds up to 360. So B plus D must equal 180 because of angles in quad. Actually, let me zoom in. Angles in quad equal 360. And therefore, you have now proved that 180 equals A plus C and B plus D equals 180, and like that. So I want to move on to the next one now, because I don't think this is as difficult as the other ones. What did you have to do? The construction was to join the radii. Then you wrote out each of the angles in terms of the matching double size one. Then you used the angles in a revolution to add to 360, and that was it. So give me a score out of 10 for how well you think you understand this theorem now that I've explained it. I'm just going to do one more tonight. I quite like this idea of just seeing, okay. So again, remember, you can go back and re-watch this video, and all I'm trying to show you is the 4 steps that every proof has, and then where do you need to memorize? You need to memorize the construction, and you need to memorize what angles go with which theorems go with which proofs, and then also to show you some exam questions. Okay, let's go on to one more. And this is going to be the last theorem we cover for today. And it's probably angle at the center, twice angle at circumference, and tan chord are the most popular theorems to be tested on exams. So if we look at this, look at the angle between the tangent and the chord is equal to the angle in the alternate segment. We don't go through the middle here. And let's just look at the proof to see what it actually says. So if we look at this theorem, what are we given? Okay, what are we given? It's a tangent, and we have points on the circle. So we have a tangent, and then we have some points on the circle. We need to prove that A1, which is this one over here, is equal to B. That's what we want to prove. That's what so we're given this, that's what we need to prove. Now, the first time you start learning is the construction. And what is the construction? It's to construct a diameter, but the diameter must go through the center point, but that's not enough. You have to create a new point and connect it to the point over here. And I think about completing the butterfly. You need to complete the butterfly so you have a full butterfly in your cyclic quad. So you need to learn that. Now let's look at the proof. So step 1, the proof. A1 plus A2 is 90. So the first theorem that you need to use in here is the tan radius theorem. So that's 90 degrees, tangent, and then a radius. then you know that the angles in a semicircle are 90. So this is the diameter. So this one over here would be 90. So that's 90 over there. All right, now we have to go and look at this angle over here. We call this angle F. If you look at angle F, how would you find, actually, let me write down here, angles in semicircle is what I've used along the way. Now, to work out what the size of the black dot or angle F is, I'm going to use sum of angles in a triangle. And I'm going to say that this F is 180 minus 90 minus this little angle down here. What's this little angle called? That's called A2. So we're going to say that F is equal to 90 minus A2, sum of angles in a triangle. Let me make it green rather. Give me a thumbs up if you understand how F is 90 minus A2. So if you look at F, look at the triangle that you have. You have this triangle here, and you go 90, you go 180 minus the blue 90 minus A2, and you get the black dot there. Okay, now, what about this red one over here? I think this red one, A1, I think that this is also, so A1 is 90 minus A2. Now let's see if we can understand that. We've got the green right angle and we take away A2, so A1 must be 90 minus A2. If you understand that, give me just type A1 in the chat. If you understand why A1 equals 90 minus A2, just type A1 in the chat. Okay. But now, what I'm going to say to finish this proof off is, you know, A1 is equal to F because both of them are equal to 90 minus A2. So both F and A1 are equal to 90 minus A2. So A must be equal to F. This one over here must be equal to this one over here. But you've now got angles in the same segment. So you know angle F is equal to angle B. So for Tekel, because A2 is the one that's in common over here. So A2, if I want to get A1, I go 90, this thing here, minus the A2 over there. Okay, so what have we said so far? We've said now that, and let me just highlight this for you. We've said that B equals F. Why does B equal F? Well, because it's angles in the same segment. But now I think we're done, because if you know that this one is equal to this one, and this one is equal to this one, then that must be equal to that. And so we can say that A1 is equal to B. That's what we were trying to prove. Now, I want in the last 10 minutes to give you a chance to see this question in an old exam, but give me a score out of 10 for how you feel like if you understand the logic in this theorem. Give me a score out of 10 for how you feel the logic of this theorem. Okay, now the way we're going to get you even higher is we're going to see what an old exam question looks like. So let's go to this past exam. This was a government exam. And here is the exam. It says, use the diagram below. Notice how it has different letters to prove the theorem which states EFG equals EDF. Now, where is EFG? EFG is here, and EDF is here. Now, you've done with the given. They've given you the required to prove. What's your first step going to be? What's your first step going to be in doing this? Construction. Yes, you know what? You've already got 1 out of 5. Once you nail the construction, you're already on the board. 1-0 to you. What is my construction going to be? Can we remember what was the first part of the constructing? Construct a diameter. So I'm going to go, and I need a point. So you know what? Let me just make it H. So I'm going to say construct what? Construct FH as diameter. And then what's the next thing? After I've done the diameter, I need to do something else. I need to join H to E. Yes, I like that. Okay, step 1 is complete. The construction, 1-0 to you. What is my next step? I am indeed allowed to make up letters. If I didn't make up letters, and I didn't have to use H, I could have used something else, but I needed a point on the circumference. Oh. So Kristen, you wouldn't join HD because of the way that you're trying to do this. So you would rather join it. You would rather join it because you're going from this side to there. That's why you would rather join it to the opposite side. Okay. So step 1 that I remember was to say that HFG was 90. What is the reason going to be for that? What is HFG? What's the reason I use for that? It's going to be tan perpendicular to radius. And then what is the other one I need to say HEF is equal to 90. And why is that equal to 90? I remember that's the diameter. So it's going to be angles in semicircle. So we know that and we know that. Okay, now what is the next step after that? What is the next step after that? Yeah, FG is a tangent, yeah. Didn't we find, you know what? I think it would make life easier if we made F1 and F2. So I'm going to go back to my construction. I'm going to say label F1 and F2 because it just makes my life easier if they were labeled F1 and F2. Otherwise, I have to say EFG, HFE, and so on. So label F1 and F2. Let me make it a bit clearer so everyone can see this. So this will be F1, this will be F2. And I want to say that H is equal to, and let me even put this in so you can see it. So we had this before. H is equal to what? It's going to be equal to 90 minus F1. And that's going to be sum of angles in triangle. And then what is F2 going to be? Now I've just labeled this. So F2 is also going to be 90 minus F1. Because you can see F2 is over here, right? Like, got that one, 90 minus F1, and we have that. I'll just probably say actually complementary angles. Complementary angles. Okay, but now if this one is equal to, let's have a look. So we got F2, so now we know that F2 is going to be equal to H because they both equal 90 minus F1. Yes, Tato, you need to match what you're doing there. So I want to suggest, so F2 is 90 minus F1, and we know that this one is equal to that one over there. What's my last step going to be in the proof? So we've proved that this one over here is equal to that one there. We now need to say that H is equal to D, and that is going to be angles in same segment. And then just to make sure we write it in the language they want, D is actually EDF. So we can say, therefore, and EFG is actually F2. So we can say, therefore, EFG is equal to EF, and that's proved. And what we've basically done is we've said, look, this one over here is equal to this one over here. That one over there is equal to that one over there. Therefore, these two have been proven. Okay, I can resend the link to the notes, no problem. Let me go and find that quickly. And let's resend the link. Okay, now everyone, what I was hoping to show you today is that proofs don't need to be, they do require some learning, but it's not like we should obsess about them, but you should learn the constructions and do learn like what basic structure goes with it. But in reality, you can get, even if you don't get full 5 out of 5, you should be able to get at least a 3 out of 5 or 4 out of 5. And my hope today was that I just started to show you how they follow a particular process. And that often in exams, if you look at past papers to practice, that's probably the best way to practice proving theorems. And I hope today has made it just a little bit easier in terms of the structure we use. Kia, can you just put a link to the poll so that our students can let us know how they found the pace was today? And yeah, good luck for the rest of the week. I will see you on Wednesday for our last circle geometry session. And remember, there are lots of recorded videos that you can watch to keep topping up your knowledge of circle geometry. Cool. For Tejo, the next thing is trigonometry.